what it looks like. Homework 2 grading is going to be starting right now. And as you probably may have seen, there's a homework 3, so, which is due in a week and a half. So all the questions except for the last one should make sense already. The last question should make sense today. So that's a one question on each, so the questions are already and again, this is going to be, I will say that this one is going to be a little bit harder than the other two, mostly because as we've seen, reasoning with greedy algorithms is a little more tricky. It's not as formulaic. So give yourself some time and start thinking. That's number one. Number two, and this is sort of an unfortunate thing that for various reasons I could not, work a way around. I will not be here until next week. I have to go to India. So so we won't have class next week, but I'm going to try and do those, put out lecture notes. So either in this format or ask you to read these. It's not the same thing, I admit, it's not ideal. But I will try to, as far as possible, to give you reading material to sort of keep things up. So there's one thing, so what I want to talk to you about is flows and how they are applied in various contexts, and I will try to give you reading material to get you sort of some similarity to this. And when I come back, we'll review some of that material. So my hope is that you're able to at least read the material and sort of get some sense of it. I don't expect this will replace lecture, but I'm hoping that we can use that as a basis for a quicker discussion of the material and we'll continue on that. So I apologize for this. It's not something I would like to do. But I will try to sort of make up with giving you material to follow this. And I will be on, I will be online, especially during this period. I will be online for questions about the homework. So, I will try as far as possible to answer very quickly, so that even if I'm not physically there, I'll see around that. Just for homework 3, I suspect you have questions. And so there will be time. I deliberately moved deadline to not, just be a Sunday night deadline. So there's time for you to come and meet with me as well once we're back. So if other questions about the homework, then we hopefully some time for you to resolve some of your doubts. So that's hopefully will mitigate some of the pain of not having the class of next week. Right, so that's that, and that's that. No, I think that's it. So before I just start now, so again, I will put up homework 1 solutions tonight. Homework 2 is being graded right now, and I will, and homework 3 is already out. So there's basically 5 questions. 4 of them are on greedy algorithms, and there's 1 on flows, which is sort of a basic, very simple flow question, as you'll see once we talk about today. And hopefully it'll cover maybe it should do. Some of the greedy questions are tricky. From money is bad news. So all right. So let's continue with our discussion. If you recall, last time we were talking about flows, and we were talking about this relationship between flows and cuts, the idea that if you have a cut is a set of vertices, edges, if you delete them, separates the graph into 2 parts. And ST cut looks at a specific vertex S, a specific vertex T, and looks at a set of edges that if you remove would disconnect S from T. Then we talked about flows and the idea that you flow water through pipes, which are edges, which have capacity, which are the numbers of them, from the source to the sink. You don't lose or produce water anywhere else except the source and the sink, and you want to see how much water you can push through. And then I said that these 2 things are sort of related to each other in some way, that clearly, every flow is at most the size of a cut, because you can't push more flow than the capacities allow you. So when I say cut in this case, I mean the sum of the capacities of the edges of the cut. And so what I want to show today is an algorithm that we will use to try and compute the max flow. And we will argue that the algorithm actually does compute the max flow, not by reasoning about optimal flows, but by saying that as a result of the algorithm, I can compute a cut. And since all flows are less than all cuts, if I have a flow and I can produce a cut of the same value as the flow, there is no way the flow could have increased, because no flow can be more than any cut. And if you remember the picture from before, right, what I'm going to show you is that in order to show that my flow is maximum, I'm going to show you there's a cut of the same value, which means there's no way the flow could get bigger. Okay, so it's a different way of showing that something's optimal, but it's a sort of a little sort of initial preview warning, if you wish, of LP duality. And this is sort of LP duality in a simple form where it's a bit more accessible, but it's really that's what's going on. Okay, all right. So let's start with that now. And so let's just take a graph. We could very well just take this graph itself. A cleaner version of here somewhere. So let's put this graph here. I think there was one edge missing, right? One edge capacity missing. Yeah, right here. I don't know. Let's put it up. Okay. The source of the sink are marked. And the goal now is to compute a maximum flow through this. And we've talked about the idea of doing a greedy strategy, and we sort of played with an example earlier. We said, okay, well, maybe it might be right, but we're not quite sure. There's no way to really tell if the greedy is going to give an optimal solution. And that's one of the problems that gets with greedy in general. What I'm going to describe to you is a different procedure that you could think of it as greedy, but with backtracking, but in a systematic way that allows you to see it. So let me explain. So the idea is to push flow from the source to the sink. And, you know, water adds, right? So if I push some water, I push some more water, they all combine. So I can think of the algorithm that I want to design here as an algorithm that says, okay, let's push some flow from source to sink. Let's push some more. Let's keep pushing as much as we can. The key, of course, is to be able to modify the graph in between pushes to allow for the possibility of changing our mind and so on. And I'll explain what that means. So let's take here, if I want to push flow from source to sink, what I'm saying is I would like a path from source to sink on which every edge has a non-zero capacity to be filled. Because if that means that there's a set of pipes and there's something empty there, and I can push some water through, right? So if I want to find a path from source to sink in this graph, that's very easy. That's a breadth first search, or a depth first search, or whatever you want. Take your favorite search procedure. I want to find a path from A to E. So someone give me a path from E. Any path, I don't care. It can be as convoluted or as simple as you want. A, B, C, D, E. Very good. So one path from A to E is A, B, C, D, E. Okay? So now we found a path, and we want to push some flow on it. Well, you want to maximize the flow, right? If we're being greedy, what should we do? We should look at the maximum amount of flow we can push along this path by looking at which edge has the smallest capacity. In this case, which edge has the smallest capacity? CD has a capacity of 1. Okay, so we say now that CD has the min capacity, right, of 1. So we push 1 unit of flow on the path. And this path is very special. We're going to give it a name. It's called an augmenting path. Again, it's not that fancy a name. Basically says I am augmenting the flow along this path. And so this algorithm is going to be basically constructing a series of augmenting paths in order to update them. And every step it adds a bit more flow, and a bit more flow, and a bit more flow. That's what the whole algorithm looks like. And the whole challenge is finding these augmenting paths. So we found the first one. That's great, right? And we can update it. And so it's easy to update because you can now say, well, the edge AB used to have capacity 10. What's its capacity now? 9, because I pushed 1 unit of flow. The edge BC used to have capacity 7. It has now capacity 6. The edge CD used to have capacity 1. It has capacity 0. DE used to have capacity 2. It now has capacity 1. In other words, we can take every edge. So let me draw an edge. So this is some edge between U and D, right? And it had capacity C. And I decided to push F units of flow along this edge, right? So in order to correctly update my graph to store this information, I will now have to transform this to easy enough, right? Yeah. It turns out that this is not quite enough. This will basically give us the greedy strategy we saw that we did the path and we remove some capacity. We want the ability to change our mind. We want the ability to say, well, yeah, I pushed F units of flow, but maybe that wasn't quite right. And it takes some of that back. And the way to think about that is to say that So think about it this way. Suppose, let me write down the numbers here. Right? So let's say, let's take edge BC. Okay? So edge BC had capacity 7. We push 1 unit of flow through it. Right? And according to our procedure, if we look at BC now, it has capacity 6. Imagine that you have short-term amnesia. You did the flow thing, you went away for 10 minutes, you came back and you forgot what you had done. And you saw this new graph, you said, oh, okay, there's an edge, it has capacity 6. You don't know that it only had capacity 6 because you decided to put 1 unit of flow through it. You're just seeing a graph of capacity 6. Capacity 6. In other words, you don't have enough information to change your mind. If all you do is store that it has capacity 6. You need to say somewhere, well, actually it was 7, and we kind of pushed 1 through it. So in order to do that, you have to somehow encode this information. And the way we're going to encode it is in a very strange way. We're going to encode this by saying that there's another magic new edge that has just appeared, which is going backwards from C to B. And it has capacity 1. Not flow, it has capacity 1. Why am I saying that? What could that possibly be? If I'm putting an edge from C to B with capacity 1, it means in this new graph, I am allowed to push 1 unit of flow from C to B. Not more, but 1. What does that mean if I caught my memory back? It means I changed my mind about that flow. That 1 unit of flow I pushed forward, I want to take that back. The fact that I put a capacity 1 is telling me, look, I only push 1 unit of flow. I can only take back 1. I can't take back more than 1. But the fact that the edge exists means I have this memory of what I did earlier. And of course, I drew it here in green to emphasize it. But in the graph, it's just an edge. There is no way for you to tell that, this was the real edge and this is the fake edge. There's no such thing. It's just an edge. Right? So the flow procedure does not know that this edge was just manufactured because I put a flow. It's just some edge. And what you get, and what we call this is, again, we call this we call this essentially a residual edge. It's the residue of what you do after you run a flow augmentation along an augmentation. Okay? So far, so good? So now our strategy is going to be the following. As before, we have the graph. We're going to find an augmenting path. And we're going to push whatever flow we can along the augmenting path. And now every edge is going to be going to be modified, so I put a back edge of flow to represent the idea that I can change my mind after that many minutes of flow. So I'm going to replace every edge in this. So in my original graph, here, right, okay, I had these edges here. What's going to happen now, remember I pushed 1 unit of flow, right? So this is going to become 1, 1, 1, 1. And now these things are going to become 9, 6, 0. Okay. I have now created a residual graph. So I've gone from G, I update one augmenting path, and now I get is GF. But this is also a graph. It has capacities, it has a source, it has a sink. I could do the same thing. Find an augmenting path from source to sink. Ignoring the fact that these edges are special. They're just edges. And then run this on. And so I'm going to do this again, again. So is the overall arc of the algorithm clear? That I will confine an augmenting path in any way I like. In fact, there are many different algorithms you can pick now based on how they choose your augmenting path. And then once I have the augmenting path, I'm going to augment the graph and update it to get the residual graph. Right? And that's it. And now, oh yeah, obviously I'm going to maintain the flow that I've currently calculated. So the real question is, what happens when you keep doing this? How long does it take? And do you actually get it? Notice what has happened though. In the process of doing this update, we can no longer update along the path we updated before. Why? Because the path A, B, C, D, E no longer exists. The edge has gone backwards from D to C. In the directed path is blocked. Essentially what this is saying is, look, there was only one edge here, that path got blocked. And that's always going to happen, right? Because if I always look at a path, look at the minimum capacity edge and push that much flow, it's going to block that edge. It's going to go away. It's going to start pointing backwards. Right? Okay. So what do we do next? We find another path. So let's find another path from A to E. Anyone you like? A-H-I-F-E. Very good. That's a path. A-H-I-F-E. Okay. What is the, so let's write this down. So in the meantime, tell me what the minimum capacity edge is. What's the minimum capacity edge? So there's a 5, a 3, a 2, and a 4. The minimum capacity edge is 2 between I and F. That is the amount of flow we're going to push. So we push that much flow. What's going to happen? This is going to become 3. This is going to become 1. This is going to become 0. And this is going to become 2. We're not done yet. I'm going to do these edges in black now because they're just edges. Well, okay, let me do it in green. Just remember, they are just edges. This is going to be 2, right? This is going to be 2, 2. Oops, sorry. And this is going to be. Okay? Graph is getting messier and messier, but you get it. Yes.
Yeah. So after the first transformation, we can always have a path A, H, G, D, then from D to C, and so you can
good. A, H, G, D,
and then C.
C, and then what? Where to get to E now? Wait, where to get to E?
No, not E. A, H, G. So I'm just asking that we can have a path that goes from E to C because we have a path.
Yes, but it's not an augmenting path. Why? An augmenting path has to start at A and has to end at the sink.
Yeah, so we can go from C to I and I to F to E.
Yes, this is a perfectly valid augmenting path. Your path could have been A, H, G, D, C, I, F, E. Well, no, it's not. Not anymore.
Yeah.
It would have been before this, but not anymore. Why not anymore? Because I to F no longer exists as an edge. But you're absolutely correct, and that would have been a good one to try. And what would that have done if you had done that path? It would have reversed our decision, at least along the edge C to D. And here's where a bit of magic comes in. I kind of wish we had picked that path. I wish I thought of that. But we chose a path from A, B, C, D, E. If we chose the new path that you proposed that goes backwards, we're not revoking our decision to do A, B, C, D, E. We're merely revoking that one edge. And that's the beautiful thing about flow, that you're not actually, even though it looks like you're coming up with paths, you're really just pushing water out in different directions. And that's why this backtracking is possible. Because you're not saying, okay, I'll try this path and try that path. Okay, that path is bad. Because there are exponentially many paths between a source and a sink. If you think about it, in a graph of size n, you can have exponentially many paths. I'm not changing the paths themselves. I'm just changing pieces of them. And that's the key to being able to change your mind. Okay. Well, is there a way we could try to? We could do another path here, which does let us change your mind. So, for example, it's going to get horribly messy. But let me see if I can make a copy of this. So we could go A, H, G, D, C, B, right? Okay, then I'm still stuck. That's not going to help me.
You have to knowledge there.
Yeah, I don't know easy way to do this. Not right now. It might come up later, but at least right now it's not that easy to do this. So now we have our second augmentation. And now you can say, okay, how many units of flow have I now pushed from source to sink? The first pass pushed 1. The second pass pushed 2. It doesn't matter whether I go through things that I change my mind about. The flow is always increasing. Because I'm always pushing flow from source to sink. So if you think of the flow, it's constantly building up, which is a good thing, by the way, right? If you want to do things like estimate the running time of an algorithm, you want to be sure it's always making progress. So even though things might be changing their mind about how they're pointing, the algorithm is always making progress, always getting higher and higher and higher and higher. Right? Okay. When would this process stop? I've given an algorithm, I said, okay, find an augmenting path from source to sink, augment, update the graph, find an augmenting path from source to sink, augment, update the. When would I stop? Sorry? There's no path. So this will stop when I no longer have a way to get from the source to the sink. And if you think about it, now that hopefully maybe you have a bit of intuition about these ones, imagine as I start pushing more flow out from A on its 2 outgoing edges. What's going to happen? There should be a way to do. What's going to happen when I do that? What's going to happen is the forward edge from A to H will keep getting smaller and smaller in capacity, right? The forward edge from A to B will start getting smaller and smaller in capacity. Eventually, maybe, I'm not saying it will happen, but it could happen that all the edges from A have 0 capacity and everything else is pointing back in. Now, if that were the case, that would be actually pretty good, right? Because that means every single edge out of A has been saturated with flow. Obviously, you could have done much more than that. And therefore, you're done. But of course, it could happen that I stop somewhere. I can no longer get from A to E, but I can get from A to other things. And then the question is, okay, well, I can get from A to somewhere, but I don't seem to be able to get to E. Am I sure that I've stopped at the actual maximum? Right? Any iterative process, right? You have to ask yourself, well, first of all, does it stop? And does it stop in the right place? Now, it's not clear that this will stop at all. We have to think about that for a second. Maybe we should think about that for a second. Let's assume all the capacities are integers. Okay, that's very important. Can we say this always stops? Or if you have to argue that this always stops, how would you argue? So in other words, we're not worried with the running time, we're worried with the number of iterations. How do we prove a bound on the number of iterations of this process?
Max flow is some O star.
Sorry?
The max flow is O star, some optimal flow max. And every time if we push, we increase by 1.
Okay, say that sentence very carefully. Every time you push, you increase by 1.
At least by.
Why?
Because the minimum, the edge capacities are integer.
Right?
And
If it's not 0, it has to be 1.
it has to be 1.
If the minimum capacity is not 0, it has to be at least 1. So at every iteration, you push at least 1 unit of flow from the source to the sink. Right? Okay. That doesn't, okay, so fine. So now, okay, I've made a good observation. At every step, I make some progress. When you're thinking about how to show that something stops, you should say, okay, I'm making some progress. That's good. And if I have to get to there and make one set of progress, I'll eventually get there. But if the wall is not there, there's no there to get to. Is there a wall? Or if you go to the algorithm, is there a point at which you can be, that you know you will not get beyond?
Since the capacity of the edges are finite, then it has to stop, right? Because
Good, you can say something even stronger than that. But you're right. The capacity edges are finite, it should stop. Can you say something more precise than that? Even more precise. Think of the source.
So we have maximum capacity which is constant, right?
What is that maximum capacity?
So if we get the best of all the paths we are having, so if we have a maximum number.
Can I look at my input graph and write down a maximum capacity without thinking at all?
Okay.
Yeah.
So
Max of the outgoing edges from the source.
The max of the sum of the sum of the outgoing capacities of the source is clearly a limit. So it's like this. I'm just taking one step at every iteration. The distance from my source to its full capacity is whatever sum of the edges. Therefore, I cannot take more than that many steps before I must reach it. So remember, two things are playing a role here. There is a bound, and at every step I take a good amount of progress. I take 1 unit. If you get rid of these things, this is not true. By the way, if you allow for fractional capacities, this algorithm will break. Not only will it break badly. That's a very cool example of this. It will not stop. So let's put it this way: it will take infinite time to stop at the wrong answer. if your capacities are not integers. This is an example. It's a beautiful example of this.
Why do we only talk about the outgoing capacity from the source, but not the ingoing capacity to the sink?
Good.
Yeah.
Very good. You can be even more precise. It is the minimum of the sum of the capacities outgoing from the source or going to the sink. And you're absolutely correct. Same reasoning applies. You're taking one here, you're taking one there, right? So now we're happy at least that we feel that this thing converges, right? It stops somewhere. That's step one. Step two is, does it stop in the right place? Okay. So let's just sort of write this down. So observation one, each augmenting path adds 1 unit of flow if capacities are integers. 2, there is a bound on total capacity out of source or in to sink. Let's call it C. Therefore, the number of iterations is at most C. Okay? Okay. So now we've got to this point where we can no longer reach the sink because our edges have sort of flipped backwards. So let's draw what this looks like. So we have the graph, and we have the source here, and we have the sink here, and this is the set of things we can reach. These are all the vertices we can reach, and we can no longer get beyond that point. Okay. And this is the residual graph we have. So let's look at any vertex at this point. Okay. Can we say anything about the edges incoming and outgoing this vertex? So in other words, does this have any edges? Okay, let's call this side. Call this side A and let's call this side B. Does the blue vertex have any edges to any vertex in B that have non-zero capacity? No? Why not?
Because you put, that's the cut, right? So you essentially just push this capacity through A and B.
because if we had, then there would have been an augmenting path, and then we would have.
Well, there is no augmenting path to P. But more importantly, we said this is the boundary of what S can reach. If there was an edge from that blue vertex to something in B that had non-zero capacity, then by definition that should also be in there. So for every vertex on the boundary, right, that's in A, every outgoing edge has capacity 0. Okay. If every outgoing edge has capacity 0, think of how we constructed this residual graph. What about the reverse edge? But how much will it have?
The original
Original what?
maximum capacity.
The original capacity of that edge, right? Because basically for this edge now, we have a picture that looks like this. This is U belonging to A. This is V belonging to B, right? It has capacity 0, and therefore its reverse capacity must be C. Another way of realizing this is that when we do this transformation, the sum of the capacities along the two sides is always constant. It always is C. So if one goes down, one has to go up. All right. But that also means one more thing, by the way. If the outgoing capacity is 0 and the incoming capacity is C, how much flow have I pushed along this edge? I pushed C flow along this edge. So along this edge, the flow is the same as the reverse capacity. Okay. So now, let me define a cut as the edges that are going forward from nodes in U to nodes in nodes in A to nodes in B. Okay. Yeah? The cut consists of all those edges. Is this a cut? Well, more particularly, is this an ST cut? If I removed all these edges, would I disconnect S and T? Well, this is by definition, right? Yeah. These are all the edges that I can no longer get. I can't reach T with these edges. If I remove them, all I can reach from S is the stuff in A and nothing else. I cannot reach T, therefore this is disconnected S A from, right? So this is a cut. It's also an ST cut. What is the capacity of this cut? Some of the capacity is along those edges, right? Okay, what is the flow in this graph? It's the sum of the flows along all these edges. But what do we just say? The flow is equal to the capacity. So in other words, we have constructed a situation now where the sum of the flows along these edges, the max flow, is equal to the capacity of the cut. So we have a flow of value F, we have a cut of value F. Because the flow has to be less than equal, the value of a flow has to be less than equal to the value of a cut. Okay, so let me write this all down. So what did I just say? So this is for every edge from A to B. So define the cut. Right. S is an ST cut, and the capacity of S is equal to the sum of all edges in S, the capacity of that edge, which by the above argument is equal to the flow from A, because all these edges have been saturated. Right? There is no extra edge. Okay. So all edges going out have capacity 0, all edges coming in have capacity 0. Yeah.
Does this thing still hold if there is an original edge from the B part to the A part? And like in that case, we would
suppose there is an original edge from the B part to the A part.
Yeah.
Okay. Is there any flow along the edge? Suppose there was flow along the edge. then in the residual graph, what would you see? You will see a back edge going from A to B with non-zero capacity, which we know cannot happen. So this is a good point. All the edges that originally went from B to A must have zero flow on them. All the edges going from A to B must have maxed out flow on them. And I'm glad you asked this point because I omitted, I forgot to mention this point. This is an important point. That if you look at all the edges crisscrossing A and B, the edges from B to A have nothing on them. The edges from A to B have all the flow on them. And that's why the flow equals the sum of all the flow edges from A to B. Yeah? Because otherwise the net flow would be the flow going out minus the flow going in. And I was saying there's no flow going in. Right? So okay. So is the capacity flow A to B? Because flow to A to B minus flow from B to A and there can be no flow here, else there exists a residual edge of greater than zero capacity from A to B. And we know that can't be. So therefore, the capacity so continuing this argument, the capacity of S is equal to the flow from A to B, right? Which is the flow in the graph, right? Which means that we now have, which means that we cannot get a larger one. Okay, so think of what has just happened here. I wanted to show that the flow was maximum. I did that by constructing a cut very carefully, by looking at the flow, saying, okay, I'm looking at the flow, I'm going to see what's reachable from S, I'm going to look at all the edges going out, and that's going to be my cut. I constructed a cut from the flow that has the same value as the flow, and therefore can conclude that the flow can't be free. Again, the language of LP duality. I had my primal program, and I used it to construct values for the dual program, and I showed they were equal. Again, if this doesn't make sense, don't worry, it will once I explain it. But if you have seen linear programming before, that's what the connection is. So this is a very different way of proving that something is optimal. We didn't use recursion or induction or greedy to optimal relationships. We said, okay, well, this is optimal because I produced this thing, and they have to be true. It's a very weird way of proving optimal. That's what makes it cool. Yeah.
How do you prove that it is a min cut? It is a cut.
Okay, it's a cut. Suppose I could get a smaller cut. How did I get this flow? Every flow, remember that picture? For me, primal dual methods always follow this picture. Every flow is less than every cut. If this was not the min cut and it could go further, I just produced a flow that was bigger. I actually have the flow, right? So there's no way I could get a smaller cut. How did I produce this flow? This is a feasible flow. Every flow augmenting path was valid. I did everything correctly. I did not violate any capacity constraints. So if I have a valid feasible flow and it matches the cut value, I cannot make the cut lower because every flow is less than every cut. Because the flow on an edge is at most the capacity of that edge. You see the argument?
Okay, so we are proving that we are having the max flow on cutting.
We're proving that the flow is maximum because it corresponds to a cut of the same value. You could also think of this as saying, I'm proving the cut is minimum by constructing flow, but we don't know how to do that, right? So for example, if you flip this around, so okay, I want to compute a min cut. You could produce a cut somehow. How would you show that it's minimum? You would show that you can push that much flow through the graph. And I haven't told you how to do that. That would be a completely different way of thinking about this problem. But what I'm saying is, if I want to solve the max flow problem, I can solve it by constructing a cut of the same value. Any other questions? Yes.
So this problem always has solution.
Yes.
Something
Well, I'm covering the maximum flow, so the maximum always exists, right? It could be zero, but it always exists. So when you say it always has a solution, I'm not sure what you mean.
We know for sure that there happens that is equal to the flow.
Yes. I mean, in this particular case, I just showed it to you. That for any flow, I can construct a cross. So, in other words, take a flow that has terminated, that I can't augment any further. Find the set of vertices reachable from S. Look at all the edges going out from that set to the stuff connected to T. That's my cut, and it has the same value. This is the proof that these two things are equal. I've demonstrated. I can show that flows are less than equal to cuts. This part we can already see because every flow is less than. You only flow as much as the capacity of the edge. What we proved is that in fact you can make them equal by constructing the explicit cut.
Yeah. The question is there any cases that I am stopped and I cannot find a solution?
Yeah.
Is it possible if I use this algorithm?
So remember, I ran the algorithm and the algorithm stopped somewhere, right? I don't know where it stopped. It just stopped somewhere for any input, right? And then I said, okay, it stopped somewhere. Okay, let's look at the set of things reachable from the source, right? That's what I just did. I found A and B. And then I said, okay, I got A and B. Let's look at all the edges across the cut. And add up the capacities. And then I proved that the sum of those capacities is equal to the flow. So the answer is no. If this algorithm stops, it is guaranteed to find the max flow because I know it can't get me further because I have found a cut. The cut, remember, is a structural property of the graph. It has nothing to do with the flow. But by looking at what the flow did, I have produced this cut, which is true for any other flow I might come up with. It's there. So if I'm trying to be smart and come up with a different algorithm for flow, it has to reckon with the fact that I cannot get any bigger than this cut. Because flows are less than cuts. Yeah.
Also, the max flow cannot be less than the cut, right? It has to be equal to the cut.
No, I'm not saying it has to be equal. All I'm saying it has to be less than or equal.
If it is less than the cut, then there is some possible max flow, right? Then you can push through the cuts if it's less than.
That's an assertion. All I said was, it is clear that a flow is less than a cut value because flow is upper bounded by the capacity of an edge. Whatever flow I push on an edge, it has to be less than that. That's one thing. To show they're equal is non-trivial. I just proved it now. That for any flow, I can produce a cut of the exact value. It's not an obvious statement. I had to prove it. This is the proof. The proof is that take the flow, construct the set of edges. Oh, look, the set of edges has a cut value that is equal to the flow of the edge. This is not an obvious statement. In fact, this is the statement of strong duality. You have to prove it. It's not always true. For many problems, it will not be true.
Yeah, if the sources are like pushing less flow.
No, not on flows. Different kinds of problems.
No, I'm saying it would be not true for flows where the source is pushing less amount of water.
No, it's always true for flows. For max flow is equal to min cut, always. If I have a crappy algorithm, that's one thing, but then I haven't found a max flow. The max flow in a graph is a property of the graph. It's not a property of my algorithm. The max flow is equal to the min cut, and this algorithm happens to produce the max flow. That's what I'm saying. So I know this, yes.
So what are the properties of the graph that you have before starting this process? That each have the essential directions, but it should be bidirectional circuits or
As long as the capacities are rational, this will be fine.
so bidirectionality and self-loop.
So as long as the capacities are rational, the max flow will be equal to the min cut. I have to think about what happens to the irrational. It's not completely obvious. Although, yeah, I have to think about that. I think it will still be true. No, this will be fine. It's fine. Whatever graph you have, whatever capacities you have, the max flow is equal to the min cut. Whether this algorithm will work, you need integer capacities. This will not work if you don't have integer capacities. But the statement that the max flow is equal to the min cut is always true. Yes.
So, just one quick question on if it's a flow problem, we need ST min cut, right?
What do you mean you need an ST?
We have to disconnect the source and then the
Correct.
sink,
Right.
because that may not just.
Right, so the ST max flow is equal to the ST min cut.
Yeah, so it's the ST min cut, not
Right.
just the min cut. But-
That's a good point, and I should be more careful about that. It's the ST min cut.
Okay, and then if we have a undirected graph, right, we can claim that it's just a min cut.
If you're an undirected graph, you don't have a flow problem.
Okay.
To specify a flow problem requires a directed graph with capacities on edges and a source and a sink.
Okay.
A flow problem is not specified till you have that.
Okay. And then,
If you want to find a global min cut in a graph, that's a different question.
okay.
But by the way, you can try it. You can find a global min cut by finding the ST min cut for every pair of edges, every pair of vertices S and T, and take the best one.
Okay.
So you can solve the global min cut problem by using this.
Okay.
It's not the most efficient way to do this, and we'll look at a better way of doing this later in the course. But you can solve it using this. You just try all possible pairs of S and T. One pair will be the right one. Yes.
If we have a direct graph and we want to use this algorithm, so we can
Wait.
find
Use which algorithm to do what?
the algorithm for maximum.
To do what?
For the flow problem.
To do what?
To find the max flow and min cut. We can
You can't find a max flow. The graph is not directed.
Well, I have the indirect, but then I can define it for each edge have two directions, one and the end.
Yes, you can.
Then we can use this.
You also need capacities.
Because the command.
Does the undirected graph also have capacities in it? Maybe it does, in which case you put bidirectional edges. Yeah, you can do that. Yes, that will be fine. But that's my point. To get to a flow formulation, and this is going to come up when we talk about applications of flow. So one of the reasons I said we want to study flow algorithms is not because you're always going to compute min cuts or max flows. It's because the idea of a flow can be used to solve other problems that have nothing to do with flows. But in order to do that, you have to take your problem and convert it into a graph that's directed, that has capacities, and has a source and a sink. And that's one example of how you might do it. And we'll be seeing, I will be providing you many examples of this. Actually, this, in my view, one of the most interesting parts of flows is the fact that you can use flows for other problems. And you know, a lot of time Google interview questions and stuff, they'll ask you a problem where the trick is to know flow. And if you didn't know that, you won't be able to do it because it's very hard. So dynamic programming and flows are very popular in these interview questions because they're not obvious. Yeah. Yes.
Do they try to ask questions that no one would have heard before?
There is no way they can do that because all those people at those interview places were all once here in this room. So they all open their copy of Kleinberg Tardosh or some other book and they pick a random thing. Oh, I'm so clever with us. So at this point, I think there's very rapidly diminishing returns for this interview process. But they still ask. I mean, many of you have probably done internships on that. I've never done an internship, so I don't know. But from what students come back and tell me, so they asked me about question 5 on homework 3. It's like, okay, great. And yes, they got the job, so I felt happy. But yeah, so I mean, what I've heard is direct programming for sure, and to some extent flows. But frankly, it's recording, so I won't say what I want to say. But, you can ask me later what my thoughts on whether they would ask me flow questions or not. Let's just say you have to know it to ask it. So, so yes.
This residual edge,
Yeah.
but it's not clear how it's helping us.
It's a way of keeping a memory around of what we did earlier. That's one way I like to think about it.
Basically, you can get back to the.
Yeah, but in a systematic, in a way that doesn't require the exponential blow up of backtracking in general. This on an edge break. That's kind of the rough idea. Another way of thinking about this is that you are essentially, so if you think of the vector of flows, all of these updates are feasible updates to the vector of flows, and you're basically walking in a high-dimensional space of the update. Each flow vector is a point, and each residual graph is just moving around, you're moving on the polytope, trying to find the optimal solution. So there's a polytope of constraints, and I see you're getting into stuff that I don't want to talk about. But you have a polytope of constraints that defines the feasible flows, and you're at some point somewhere, you're kind of walking around. So this is called, by the way, the Ford-Fulkerson algorithm. This is the question you're going to be asked to sort of answer in the assignment. Basically, show me that you understand how the algorithm works. It's a very simple question, but it requires to a certain extent you understand how you do the operating points. So I want to make this point.
Can you repeat that, the name of this algorithm?
Yeah, I'm going to write it down.
Okay.
Ford, after the two people who invented it. Well, after the two people who invented it last.
Is this Ford have any correlation to Ford manufacturing?
I doubt that very much.
Okay, I was just-
Good. Always good to check. But I don't know. To be honest, I don't know, but I'm pretty sure it's not. Henry Ford is a long time before that. Okay. All right. So once again, I apologize for next week's situation. I'll try to provide some meeting material so you can keep up to things, and I'll see you the week after. Yes. Yes. Oh, shit. Now the other I mentioned. Okay, very quickly. I was looking to think. So the official final exam date for this class is Monday, April 29th. What I would have liked to do was have it on in class Friday, April 26th. The problem is that because of the way the final exam scheduling works, we would not have this room basically on April 26th. So I'm talking to scheduling right now to see what we can do. Also, it would only be a 15-minute thing. Not that you would complain, but if I want to do like a 2-hour final, I could do it. So I'm sure you'd be very happy about that. So I'm talking to scheduling right now to see what would happen if I do it on the. So for those of you who are concerned, I want to have it sometime before the end of April 26th. Is that helpful? I know many people are trying to